and I welcome you to my presentation, Electrical Resistance-Based Fatigue Damage Assessment of Steels. This presentation starts with an overview about the motivation and the used material methods. And following, I will describe the results and discussion. And I will end this presentation with a conclusion and outlook. To the motivation, nickel-based high-temperature brazed joints are often used for heavily ducted components because of their high mechanical, thermal, and corrosive properties. The brazing process with a temperature of about 1160 degrees has a significant influence on the microstructure, for example, a high reduction in the dislocation density. When the brazed joints after the brazing process subjected to the high stress, this has another significant influence on the microstructure, for example, an increase in the dislocation density, which then affects the fatigue behavior. Therefore, the goal of my work is the evaluation of the development of microstructural change during fatigue by electrical resistance measurements, so that the fatigue behavior of the brazed specimens can be optimized. And electrical resistance measurements are an established method for the characterization of microstructural changes like dislocation density, voids, or microcracks, because the electrical resistance depends on those microstructure. But the electrical resistance also depends on the geometry and temperature, and therefore it is necessary to measure the geometry and temperature too for the characterization. In fatigue tests, therefore, commonly used were ex situ measurements because they are simpler. And in contrast, this presentation presents a method for the in situ electrical resistance measurements, where the geometry, temperature, and martensite are measured during the fatigue test, so that their influence on the electrical resistance can be compensated and the microstructure can be evaluated. And therefore, a complex experimental setup was developed. I will now come to the material and methods. The used material were brazed joints with a metastable austenite AISI 304L and a nickel filler. And the used brazing process was the high-temperature vacuum brazing with a temperature of 1160 degrees and a holding time of 16 minutes. And after the brazing process, this shown fatigue specimen were produced. For the fatigue test, a servo-hydraulic fatigue testing system from Instron with a maximum load of 100 kilonewton was used. And the fatigue tests were performed with a stress ratio of 0.1 and a test frequency of 10 Hertz. And in addition, the microstructure of the specimen was analyzed by using a scanning electron microscope. And for the electrical resistance measurement, a new method was developed by combining the strain measurement via extensometer with the electrical resistance measurement. And for this purpose, the electrically conductive extensometer edges were connected with cables to the voltage measurement so that the electrical resistance can be measured at the same location where the strain was measured so that they can be combined. And the DC current was introduced through the hydraulic clamps and measured with another voltage measurement over a shunt with a defined electrical resistance. So that as a result, the electrical resistance and the strain can be combined, measured at the same location, so that the strain can directly be transferred to the length change of the electrical resistance during the fatigue test. And I will now come to the results and discussion. The idea of this work is to start with the electrical resistance, and then determined from the test current and the voltage drop at the extensometer, and then compensate various influence factors, beginning with the influence of the geometry, namely the length measured through the extensometer, and the diameter measured through a two-dimensional optical micrometer. And for the thermal influence on the electrical resistance, the temperature was measured with thermocouples. And for the influence of martensite transformation, the martensite volume fraction was measured with infrared scope, so that as a result, the temperature-independent electric resistivity of the austenite was determined, which no longer depends on the geometry, temperature, and martensite, so that the microstructure changes can be evaluated. For example, the dislocation density, voids, or grain size. I will now show the evaluation on a constant amplitude test with a maximum stress of 440 megapascal. From the voltage drop at the extensometer and the test current measured at the shunt, the electrical resistance was determined by using the Ohm's law. And during the fatigue test, there's a significant increase of the electrical resistance. And after this, the influence of geometry was compensated by determining the electrical resistivity, and therefore the length of the electrical resistance measurement was measured with an extensometer and the cross-section with the optical micrometer. And in contrast to the electrical resistance, the electrical resistivity doesn't show a significant increase. Therefore, the increase of the electrical resistance comes through the geometry. And the temperature of the specimen was measured by using 6 thermocouples and for 2 separated fatigue tests, a high-speed thermography system. And the influence of temperature on the electrical resistance was compensated by using the Mathiessen's law and dividing the electrical resistivity in a temperature-independent and a temperature-dependent part. And for the following evaluation, the temperature-independent part was used. And at last, the influence of Martensite transformation on the electrical resistance was compensated. It is necessary because the used metastable austenite shows Martensite transformation during the stress, because of the stress. And Martensite has a different electrical resistivity than austenite. So the Martensite volume fraction during the fatigue test was measured by using a ferrite scope. But it was not possible to combine this ferrite scope with the previously shown measurement setup, so that separate fatigue tests were performed, and a calculation model for the Martensite volume fraction during the fatigue test was developed, which I'll not go in detail about it because of the limited time. So that as a result, the temperature-independent electrical resistivity of the austenite was determined, which, as mentioned, no longer depends on the geometry, temperature, or Martensite. So from this cause, the microstructure changes can be evaluated. And the increase at the beginning indicates a significant microstructure change at the beginning of the fatigue test. For example, an increase in the dislocation density, or a formation or deformation of voids, but it's, as I mentioned, it's not possible to clearly say what kind of this is. Well, I can only say that there is significant changes, and during the fatigue test, there are only minor changes in the electrical resistivity, which indicated that there are only minor changes in the microstructure. And to validate this result, the microstructure of the specimen was analyzed by using a scanning electron microscope and the BSE contrast. And the microstructure of the initial state was compared with the microstructure after different lifetimes, in this case, after 10 cycles and 10,000 cycles. And from the microstructure, from the initial state to the microstructure after 10 cycles, there's a significant change. But from 10 cycles to 10,000 cycles, there are only minor changes in the microstructure. And this fits with the previously shown results. And in addition, this shown method also allows the evaluation of the individual influence of the geometry, temperature, and Martensite on the electrical resistance, so that the influence of the geometry, of the temperature, and of the Martensite on the electrical resistance during the fatigue test was evaluated. And as a result, the geometry has the highest influence on the electrical resistance because of the stress ratio of 0.1 and the high ductility of the used brace material. And I will now come to the conclusion and outlook. Starting with the electrical resistance, the influence of geometry, temperature, and Martensite was compensated so that the temperature-independent electrical resistivity of the austenite was determined, which no longer depends on geometry, temperature, and Martensite transformation, so that the microstructural changes can be evaluated, but it's yet not possible to separate between them. And also the individual influence of geometry, temperature, and Martensite during the fatigue test was evaluated. And future works will concentrate on the further development of this method and to transfer it to different materials. Now the method can compensate geometry, temperature, and martensite, so that for the evaluation of microstructure change. And future goal will be to separate and quantify the individual influence of dislocation, density of voids and microcracks during the fatigue test, so that the individual influence of dislocation of voids or of microcracks during the fatigue test can be evaluated. And therefore, I'm planning with a complex microstructure investigation like SAM-ECI or use of FIB SAM-based 3D volume reconstruction models. Here are some reference publications. And I want to thank the DFG and the TR 188, especially the sub-project B01 for the funding. And I thank you for your attention. I'm looking forward for your questions.